Okay, YouTube, this is our first video in our module on solving systems of linear equations, but in 3 variables as opposed to 2. And so we have been exploring systems of equations in 2 variables with, say, just x's and y's and 2 equations. But what we want to do is basically extend this to systems of maybe 3 equations and 3 variables, such as this equation here, x plus 2y minus 3z equals 9. And equations like this here, where we've just kind of amended this z variable, and z's to the first power as well, just like our x and our y. Basically, we'll refer to this as a linear equation in 3 variables, and the general form of any of these equations is always just going to be, typically we just go through the alphabet here, but ax plus by plus cz equals d. And so a, b, c, and d, we'll just recognize that these are all real numbers and that they're not all of them 0. Many of them can be 0, not all of them can be 0. But we'll say that this is a linear equation in 3 variables, x, y, and z. And one thing we want to acknowledge is that the graph of a linear equation in 3 variables is a plane in a 3-dimensional space. So it's really weird to consider this, but if you were to think of like your x and y axes here, and I pass these through here, we say, here's our x, here's our y. Essentially, we can pass a third axis through these that is perpendicular to both of them, and this would be the z axis here. And so you could see that if we were to graph something through here, actually maybe you can't see because I'm telling you, but basically you could imagine a 2-dimensional surface, graphed through this here, and it extends in all different directions, but it never curves. And so this would be like a 3-dimensional kind of analog to what we would see as a 2-dimensional line. Usually we look at a linear equation as a line. In 3 dimensions, it's just a straight plane. Okay, it's a straight plane. So when we look at this here as a system of 3 of these planes together, recall that when we talk about a system of equations, we are looking for a common solution to all of the, say, equations in the system. And so with a 2-dimensional situation, we said the solution was the point of intersection because this is in both of their graphs, and all of the points on each of the graphs represent the solutions to that particular equation. So we say that the process of solving a system of 3 linear equations in 3 variables is geometrically equivalent to finding the point of intersection, assuming that there is one, of the 3 planes in space. And so one, kind of really, I guess, rigid example would be, what if we had all 3 of these planes meeting at, 90-degree angles? They're all orthogonal to one another. We say that the point of intersection here, this P, then would be the solution. And so we want to make sure we write a note here. We say the solution is the point of intersection. The point of intersection, okay, of our 3 linear planes, okay? And we're going to write a little note here, if it exists. And so one thing we also want to say about this is that we label this as what we call an ordered triple. So an ordered pair is this xy pair. We're going to say an ordered triple is xyz. And so we'd say give solutions as ordered triples. So solutions as ordered triples. Now recall, solutions. Again, a solution is on all 3 planes here, and so therefore is a solution to all 3 equations, say, in our system. You could see then with our first system here, what I want to do is basically determine if I give us an ordered triple, some x, y, and z ordered triple, could we determine is this a solution to this particular system right here? And so we see our very first, say, system here. These are all in, I guess, a standard form here where the variables are on the left, constants on the right. But we see x, y, and z, all the x's lined up, y's lined up, z's lined up. This would be a typical way to write this system. Looking at this, all we want to do is plug this into all 3 equations and check to see it works. So to prove that something is or isn't a solution, all we're really doing is verifying our equations when we plug this in. So we say -1 goes in for x, 2 goes in for y, -2 goes in for z. So if we were to simplify this, suppose we get -1 plus 4, this would be a positive 6 here. Is this 9? And so we would recognize that the 1 plus the 4 here would be a 3, and 3 plus 6 is 9. And so it certainly does check out in the first equation. Looking at the second equation, we would say 2 times x minus a y plus a 2 times a z is equal to a -8. And we're still going to plug in this -1 to -2 ordered triple. We just want to verify it equals -8 in this particular equation. So we get -2 minus 2 minus 4 is -8. I think that we would get a -4, and minus 4 more would be a -8. I'm just going to stop there and say, yes, that does check out. And then our last equation, we have this negative in front of our x. So we're going to put a negative out in front of our parentheses here. We say plus 3y minus 4z is 15. We just want to check this here. So if we plug in -1, 2, and negative 2, we get a negative negative 1, which is a 1, plus a 3 times 2 is a 6, plus a negative 4 times a negative 2 is a positive 8. Here we get 15. 6 plus 1 here first. Add that to 8, we certainly do get 15. So what we would say is that this ordered triple is a solution to our system. Okay? Because it satisfies all of the equations in the system. And we would look at this as if you could graph, or if you would graph this point x, y, z, negative 1, 2, and negative 2. This would be the point of intersection of all three of these planes that would be graphed by these equations here. So what I want you to do is just check this out here. See, is negative 1, negative 4, 5 a solution of this system down here? See what conclusion you can come to. Cheers.